Good afternoon and welcome to another edition of Math 208, College Mathematics for Business and Economics. Today we're covering section 4.6. We've got a couple of goals for today. 4.6 covers matrix equations. So our goals for today are to identify, create, and manipulate matrix equations, to recall and apply and get very comfortable with the basic properties of matrices, and then solve matrix equations of up to 3 variables. So let's get started. Well, first of all, we don't need that. Let's get started. For the most part, I'm going to be referencing my notes on the left. So here we go. A matrix equation extends our use of algebra. It extends our use of algebra into the realm of matrices. It makes it easier to solve large systems of equations. So from algebra, we already know how to solve some basic problems, such as ax equals b. We know how to solve that for x. We just flip things around. But now let's be very careful about what we're saying and how we're doing it. So what we're really doing and what we're really saying is we're taking the inverse of a, we're multiplying that by a, and taking the inverse of a and multiplying that by b. And that's how we solve. It's not what we do in regular algebra. We take a fraction. The inverse is actually a fraction. So you can consider them to be the exact same thing. I'm going to have to pause. I apologize. Hey, back. Sorry for the interruption, everyone. Anyways, moving on. So typically, when we're dealing with numbers in algebra, we consider a inverse to be a fraction, 1 over a. So 1 over a is a inverse. It's really the same thing. But when we do that, it's pretty clear that a divided by a is equal to 1, and then a inverse is equal b is equal to x. So that's where we get this. Now, when we're doing augmented matrices, we have a system of equations. Just recall that, hold that in your head. And in a matrix equation, we have ax equals b. This is the a, this is the x, which is equivalent to the equation. And then b is the augmented part. Okay? So, now recall some of the basic properties of matrices. And this is on page 236 of the book. We're going to need all of these to solve matrix equations. We have the addition properties. It's associative, commutative. You have an additive inverse, an additive identity. We also have multiplication properties, associative, a multiplicative identity, and if the matrix is square, we have a multiplicative inverse. We do not, and this is important, we do not have the commutative when we're in multiplication. You can't change the order. We also have some other properties, and we're going to use all of these when we're going through this. Matrices are distributive. They're both left and right distributive, but you have to maintain the order. You can't change the order. You have to keep the order that you start with. That's what we're talking about here. And then equality. So if a equals b, you can replace a with b in a matrix equation, or b with a. The same thing with left multiplication and with right multiplication. How do we solve a matrix equation? Well, you start with your matrix equation, ax equals b. You take the inverse of a, and you left multiply that on both sides. A inverse a is equal to I. Ix is equal to x. So then you have a inverse b equals x. So that's your solution. And then you multiply your a inverse and your b to get that solution. Let's do some examples right away. We'll start with the example, and I'm going to turn off my video, and I may do some examples as I'm working through it. We'll see how it goes. So we start out with ax equals b minus, so we start out with ax plus c equals b. You can manipulate this. Remember addition and multiplication with matrices, you can change the order, that's fine. So A inverse A, X equals A inverse times B minus C. And this is distributive. We're not going to use that, but it is. A inverse A is equal to I, and that Ix equals X, so we end up with this result. That's an example, just using letters. Now we're going to solve a system. And the system we're going to solve is given. We're not going to augment the matrix this time, so there's no need to augment it. We use our coefficient matrix. We create an X, that's a vector, a column vector, and B, which is also a column vector. In order to solve this, if we're looking at it, what we need to do, so we start out with AX equals B. So now we do A inverse A, X equals A inverse B. Which is X equals A inverse B. So we have B, we're looking to solve for X, and we're able to compute A inverse. How do we find A inverse? Well, there's a couple different ways we can find it. If it's a 2 by 2 matrix, we can use the determinant method, Cramer's rule. If it's not, we can use Gauss-Jordan elimination on an augmented matrix. And that's what we're going to do in this case. That's the method that we're going to use in this case. So we augment our matrix A with the identity matrix, and we're doing this in order to find A inverse. I'm not going to step through every step here. This is something that you should be able to do based upon working with augmented matrices and Gauss-Jordan elimination. Basically, you have to get into reduced row form, and then this is your A inverse. The steps that I needed to do for this are indicated. So now we have A inverse. That's great. Using A inverse, I'm going to turn the light on here. I don't know if that helps or not. So using A inverse, we can now solve this equation. How do we solve it? We solve it by multiplying A inverse by B. Can we do that? It's a 3 by 3 and a 3 by 1. So yes, we can. And our result will be a 3 by 1. So we'll go ahead and do that. 1 times 1 plus 1 times 3 minus 2, etc. Again, I expect that you should be able to do that. If not, take your time, pause the video, and work through it on your own until you achieve the results. If you don't recall how to do it, go ahead and step back to a previous video. That's okay. Let's do another example. This time we're going to solve this system. And some of these I'm picking because they're a little bit unusual cases. So we set up our coefficient matrix. In this case, minus 2, 6, 4, and minus 12. And then it's a 2 by 2 matrix, so we're going to use Cramer's method to find the inverse of it. But what we notice is right off, minus 2 times minus 12 is 24, minus 24. So we have a 0 in the denominator. Therefore, A inverse does not exist. So we can't use this method to solve. So we actually have to step back and use the method that we used previously, and that's the Gauss-Jordan method on an augmented equation. And now this you should be familiar with. We should be very familiar with this. We get it into a reduced form. We notice that our bottom row is all zeros. It informs us that we have infinite solutions. So we let x2 equal t and solve for x1, which gives us the result that x1 equals 2t minus 5 halves and x2 equals t. Let's do another example. And you can always back up on the video. You can always take more time on the video. That's absolutely cool with me. This time we're going to start out with our equation already in matrix form. But what we do need to do is we need to add these things together, combine them. Well, you have, if I were to, let me write this one down. So recall, and I'm gonna do this. So basically, this is ax plus c equals b. Okay, and we did an example a little bit earlier. So this would be ax equals b minus c. A inverse a x equals a inverse b minus c. So x, this is an a, equals a inverse b minus c. So let's go ahead and do that, only instead of using the letters that we have here, we're actually going to do that using our matrices. So this would be b, and this is c. So we subtract 5, 2 from 14, 7. They're the same size, so we can do that, and that gives us 9, 5. This would be, and then this is a and the x. We need to find the inverse of a. What happens when we do that? Well, it's actually the same matrix as it was previously. So it's minus 2, 6. It's not exactly the same matrix, but the results are the same. I switched them up a little bit, but you'll end up with the same results. So basically you have minus 24 plus 24. So you're going to end up with a 0 in the denominator. Again, it does not have an A inverse, so we have to use Gauss-Jordan elimination again. These are chosen intentionally to demonstrate when you can't use A inverse. Most of the time you're going to be able to. Using Gauss-Jordan elimination to get this into reduced row form, we find that we have a 0, 0, 23 on our bottom row, so therefore we have no solution. So this is a no solution one. I'm only going to do 1 or 2 more examples on this video. Much further, actually. Why don't we finish it? We're almost done. This is one to just practice. Practice with this, and the more you practice, the better off you'll be. So now we're going to start. This time we have a x plus bx equals c. We use the distributive properties. When we use distributive properties, remember, we're always trying to solve for x. So we have a minus b. Now x is on the right-hand side. It has to stay on the right-hand side. You can't change the order. Equals c. Now when we add a and b together, we end up with another matrix, presuming they're the same size. So this matrix has an inverse, and we call that inverse a plus b inverse. And we're going to left multiply that. And we're going to do that to both sides. A plus b inverse c. C. An inverse matrix times its inverse. A matrix times its inverse is equal to I. So we have Ix equals a plus b inverse c, which is x equals a plus b inverse c. And that is the solution to that one. We're going to do one more example. And this is the last example that I have for today. and that'll be the end of this lecture. In the discussion class, we're going to be doing a lot of handouts, a lot of in-class work. I recommend that you do and you work through in detail some of the problems that I did, and just work on examples. Do this often, get comfortable with it. So our last example is of this form, which looks very, very much like this, and that's why we're doing it in this order. So basically this is the same form. So let's call this A and this B. Only instead of addition it's subtraction. That's okay. This matrix A times A minus B, they're the same size, so that's an operation we can do. 5 minus 2 is 3. 10 minus 1 is 11. 4 minus 3 is 1. 7 minus 3 is 4. Try and find the inverse. The inverse, we're going to use Cramer's rule to find the inverse. Is that an operation we can do? 12 minus 11. Absolutely, we can do that. That's 1. How nice is that? And then recall how to find the inverse. We start out with our original matrix. We switch the A and the B. So, I'm sorry, the A and the D. And we negate the B and the C. So this is our inverse. This is our inverse matrix. So now we have X equals, and that's the same as this right here. So we have X equals, this matrix is A plus B inverse. This is C. So let's do the multiple. We're multiplying a 2 by 2 times a 2 by 1. So we should end up with a 2 by 1. First of all, it's allowable. Second of all, we should end up with a 2 by 1. When we do the calculations, we end up with 3/8. Thank you for your attention during this section 4.6. Like I say, this is something that it's good to practice a lot. Recall and often look at, if you don't remember what to do or what step to use, take a look at your basic properties of matrices. Put things in a form where using letters initially, especially as sometimes matrices get a little bit unwieldy and sometimes makes it harder to see and understand what's happening.